This is lecture 2 of analysis of algorithm. So last time we introduced some basic ideas and some wonderful examples like the Euclid algorithm and the sieve of irrefutance. So today we're trying to step into the theory, and there are some things you need to learn, which is very important. That is something you use for like the entire of your life, which is like the big O, the big O. Yeah. So let's take a look. For example, if you have an algorithm and you try to determine how much time does it take to run, you basically will follow this simple equation. So, for example, if you have an input size of n, and then your running time would be a function of n, which we don't know yet, but which would approximate equals to the number of times a basic operation is needed, multiplied by the time of each operation. It's pretty straightforward, isn't it? So we need to note that this Cn, which is a function of your input size, determine how many operations is needed, is also a function. And this function could be any kind of function, from constant to linear to quadratic or to whatever, how big it could possibly be. Yes. Uh, so here are a few examples, and in our every time our algorithm try to solve a problem, right? So for example, if the problem is searching for key in a list of n items, then what is the input size? Apparently the input size would be the number of items in the list, which is n. And then what is the basic operation? The basic operation would be the key comparison. Yeah, by the way, the basic operation normally could only be plus, minus, multiply, division, and comparison. I'm not sure, are there any other things, but basically that's what you will see. No, I don't think there are many other things. And also, multiply and division is basically a higher derivatives from adding and deleting. So basically, from computer point of view, the basic operation is basically cannot be more complicated. All right, let's continue. So every time we will meet this best case, average case, worst case, like worst case scenario. So it's like for an algorithm, what is the best case? Like, for example, when you search for a key in a list, basically you just go through the whole list and compare every item in the list to the number you're looking for, right? And you could be lucky that the item you're looking for is just right in the beginning of the list, but you could be very unlucky that the item is in the end of the list. So in this case, the best case would be 1, and the worst case would be like n, right? So the average case is somewhere in between, which is like n divided by 2. But be careful that the average case is not always equals to the average of best case and worst case, because in many other algorithms, it could be quite different. All right. So imagine, when we look at an algorithm, there are some properties a algorithm owns. It's kind of like two people are playing a game. For example, coming back to the searching a key in a list, it is as if you are the designer of the algorithm. And when you finish designing the algorithm stay as it is, and it will not change from that point. And then someone try to challenge you, say, okay, your algorithm is good or not, maybe not good enough. So you guys are going to play a game. How you play this is that the challenger will try to come out with the array, and then he will try to hide the key inside the list, so that will trouble you most, i.e. it will take the most time to search using your algorithm. All right. So if that challenger is also a genius and he find out what is the best way to annoy you and to trouble you the most, would be the worst case for your algorithm. And if he is a helper which will try to help you the most, then that will be the best case. So it's kind of not only depending how genius the challenger is or how much he wants to help you, because we cannot assume they are either the most genius or the best people in the world. So it's more like your algorithm, it's like how much they can annoy you. If you design a algorithm which works great, fantastic in every condition, then you should be expecting that probably the best case is, no, the worst case is almost as good as the best case, So yeah, I mean, we will see some examples later, and yeah, let's just keep this part going. Example, sequential search. Okay, so here we have the simplest algorithm of searching a key in an array. I could just assume you have done reading it. All right, so if you look at it, so basically it's quite simple. You have I, which set it to 0, and while I is smaller than the length of the array, and the item kept in that position doesn't equal to the key you're looking for, then keep going. All right, so traverse the list. So in this case, what is the worst case? Oh, I think we kind of talked this before, right? So worst case is like n, best case is like 1, and every case is like half. All right. So type of formulas. Right. So yeah. So we talk about, you remember this Cn, right? We have seen this before. Where we have seen it. So here, all right. Cn determines how many times of basic operations are needed, which is crucial for us to determine the execution time. So the Cn would be a function, like we said. And for example, the exact function would look something like this: Cn equals to n multiplied by n minus 1 divided by 2. And the thing here is that not every bit of it is important, which means there are some bit of it you can just overlook. For example, Cn, if we, let's share you with the whiteboard, shall we? So Cn, wow, that's ugly. Minus 1 divided by 2. All right, so if we expand it, what that would looks like would be 2 is here, and 2 squared minus, n squared minus n. And if we further get it out, it will be 1/2, which is 0.5, n squared minus 1/2, and all right. In this case, there are something we are going to see later. All right. So in real life, the n is going to be really, really big, because you know how much data we are creating every second, every millisecond, right? So when we try to analyze it, we will try to push the n to the approximate. Well, at least we assume it is a huge number, all right? So if n is a huge number, then n squared will be so much bigger than n, which make n insignificant. All right. So I mean, even you can look at here, right? So for example, n multiplied by n minus 1. So if n is infinity, n minus 1 is basically also infinity. So basically, it is n squared divided by 2, isn't it? All right. So if, as we can see, this is super, super big, divided by 2 doesn't really matter, does it? So we can approximate it into n squared count rate. Yeah. So that's how we think it through. All right. So like I said here, we can approximate to 1.5 n to the power 2. And then, like this 0.5 doesn't matter here because it's just a constant. No matter what number it is compared to n, is insignificant. All right, so we just assume there is a constant of c, which doesn't matter. So if you're thinking about the property of this formula, the property of the formula is possessed within the n to the power 2. So yeah, so the concept we are talking about is called order of growth. And yeah, there is not a whole description I can tell you about, but you can kind of feel it. It's kind of, all right. Okay, so example. All right, let's look through. I think this is pretty good. How much faster will algorithm run on a computer that is twice as fast? Basically, if a computer runs twice as fast, remember from here, from the equation, which means the C-op would be taking half the time as I said before, right? Which means the whole time, running time will be half. It's good, but we will see why it's not good enough. All right, next question. How much longer does it take to solve problem of double input size? Oh, that can be trickier. Double input size. And what it means is this n. All right, so if it used to be n, then now it becomes 2n. It is quite different, and it could annoy us more than the speed of computer, because you remember, like cn is only a function of n. So if cn equals to n to the power of 2, which is n squared, or it could be even larger, then if n, that's right. So if cn equals to n squared, then if all right, let's say if n prime equals to 2n, then what happens is the c n prime would be 4n squared, isn't it? So as you can see, there is also a quadratic increase of problems. All right. So that is, so as you can see, the input, the size of the input, so the problems, the speed, so the time taken may increase much bigger than the input size increases if it come with a very annoying order of growth like this. All right, so that kind of explains that, our computers are like twice as fast for every 18 months, but there are so many problems we still cannot solve, and we don't seem to have many progresses for every 18 months. And the kind of reason is that even if it is taking half of the time, like we see before, it just takes half of the time. But the algorithm could be very complicated, like n to the power. All right, which means the size, the trouble the input make and the algorithm make cannot be compensated by the increase of computer speed. So yeah, I mean, when you look at the, when you study the theory of computability, like, what is the class P, what is class NP, you will see there are so many things that is just uncomputable, no matter how much faster our computer are. because they are exponential rather than polynomial. Yeah. Where are we? Okay, so here are some typical order of growth. All right, starting from along the axis, you can see it is worse and worse algorithm, or we can call it a greater and greater order of growth. So here is n, so which is the input size. We can see along the axis how does the input size increases by a factor of 10, and how does a result those order of growth. If you look at log 2n, and as you can see, it doesn't increase much, although the input size n has increased like 100,000. So it is a pretty good algorithm, which means even if our input size increases a million times, we don't need to spend much longer time to do our algorithm, right? Which means, for example, if it is a searching algorithm, then it means we can find a needle in a hack really fast. However, that cannot be true because a searching algorithm could never be as good as log n. So the best searching algorithm we can mostly see in this book is n log n. So n multiplied by log n, and that is kind of the best thing we can achieve, yeah, in a searching algorithm. All right, so now you see the n, which is linear, and n log n, which is slightly worse, and n squared n to the power 3, so n cubed, add 2 to the power n. So the tricky point is, for example, for n to the power 2, n to 2 to the power m, sometimes it could be a little bit confusing which is which and which is bigger. So yeah, try to figure out, yeah, you need to try to figure out which is bigger, all right? So the last one is n factorial, which is the worst. Yeah, you can see how much it increases. Okay, let's stop here. Stop.